50% of the remaining objectives, which means you will have no additional homework throughout the rest of the semester. Oh. All right, questions, comments, concerns, choices? So, our goal today is to finish the remainder of Chapter 8. So, where we left off on previously this week, what day is this? Today is Wednesday, so that means I saw you on Monday. So you should have in front of you your guidelines for Lewis dot structures and a periodic table. So, at the end of class, or right prior to the mini exams, you likely should have this structure in your notes, where we talked about the formal charges. So when we think about drawing the formal charges or annotating where they belong. So at some point, we talked about drawing structures in brackets or other things. Brackets are more like, something somewhere has a charge. By giving an element a negative charge, that means this is where the formal charge resides on this oxygen, this one, that one, or the bromine, in this case, the positive 2. So we do want to make sure that we circle our positive or negative charges inside a circle. You don't need to include if it's 0, a 0 inside a 0. You can if that helps you as you move along. You do not lose points for that. But in this case, the formal charges just need to be annotated with whatever they are in a circle. So from here, we can start to think about formal charges in other ways. So in this case, this structure, there isn't really any variation to that. But what about if we look at CO2? If carbon is our central atom, as we count up our valence electrons and draw our structures, you can actually end up with 2 structures. So we start with this. So following Lewis dot rules, this is where you get. Carbon doesn't have octet, so we need a way to give octet to carbon. We're going to do that using double and triple bonds. So there it turns out are 2 similar structures, and formal charge is how we are going to figure out which of these structures is the more preferred structure over the other. So, in this case, I'm going to annotate oxygens that are unique, A, B, and C. C is the same because this has the exact same electronic structure. When a molecule is composed of the same element repeated, unless it has a change in some variety, you don't need to calculate the formal charge for each of these. So from here, we're going to calculate the formal charge of OA. 6 minus half of 6 minus 2 gives you +1. Sorry. For OB, we are going to get 6 minus half of 2 minus 6, and that gives you -1. So we have a -1, we have a +1. Overall, this molecule is neutral, so it could be the most preferred structure. But let's look at this other structure. For OC, we have 6 minus half of 4 minus 4. And that gives us 0. So our options are CO2, so the top structure, which has 2 separate charges, but is overall neutral, or the bottom structure, where the formal charge on all atoms is 0. It turns out that we want for there to be no formal charges. Now, sometimes that's not, frankly, a possibility. So if we have them, the formal charges need to add up to whatever the molecule charge is. So in this case, for the top structure, that is true. For the bottom structure, this is our preferred structure. And it is preferred because there are no formal charges. If there was a negative charge, like there's up here, it's not good for different charges to be on different atoms. Questions about CO2?
So if CO2 has an extra electron to have a -1 charge, would we then go to the B?
If you added another electron, like if it was CO2 minus, that would violate a lot of other rules, because in that case, there is nowhere for a single electron to go. So there are instances where we have negative molecules. We're going to talk about some of those in a minute. But in that case, not necessarily. Other questions? Let's look at some examples. So we have NO2 minus, we have HClO2, and SO3 2 minus. We're going to do the first and the third. The middle one, the HClO2, no negative charge. If you choose to do that, and we'll not do it in class, this is the bone structure of that molecule, and you can use that as such. So if I give you something where, you know me, I'm going to give you something you've never seen before. I will give you bone structures and ask you to add the valence electrons. Or I would say in words, it looks like this. We'll work on more of those as we move forward. So NO2 and SO3 2 minus. So NO2 minus, we have 2 times 6 plus 5 plus 1. And that gives us 18. So we can put our 2 oxygens connected. Once we give octet to oxygen, there are 2 leftover electrons and they go on the nitrogen. In this molecule, nitrogen does not have octet. So we need to give it octet. And we can do that by creating a double bond. We're going to do that with the oxygen here. So now we know that this molecule has a negative charge. The question becomes, where does it live? So now we're going to look at formal charge. We have A and B. So the formal charge for nitrogen is 5 minus half of 6 minus 2, which is 0. For OA, it's 6 minus half of 2 minus 6, negative 1. OB, 6 minus half of 4 minus 4, which is 0. So we have a negative charge, a single negative charge on OA. Questions?
Why is the oxygen not like next to nitrogen, like below it?
It can be.
Oh, okay.
In a Lewis dot structure, the important fact is that they are 90 degrees from one another, so you could have put these 2 things across or up and down, or frankly, anywhere you want to put them in this case. Other questions? So I will give you, 30 seconds, no, 2 to 3 minutes to see if you can come up with a valid structure for SO3 2 minus. many of you have a structure? Sweet. So for SO3 2 minus, our valence electrons are 6 plus 6 times 3, so 24 plus 2, that gives us 26. So now we're going to follow the rules, connect our 3 oxygens. So from here we've used 24, the last 2 for the guidelines go on the sulfur. So from here we can calculate the formal charges. All of these oxygens are the same, so we have the formal charge of oxygen, 6 minus half of 2 minus 6. So these all have a negative charge on them. So sulfur is also 6, but it's minus half of 6 minus 2, which gives you a plus charge. So here is a structure. How many of you got this structure? How many of you got this, but with reduced formal charges? Anyone have? Does anyone want to talk about what they got that wasn't this? I really appreciate those of you who look at me and are like, absolutely not, I refuse to talk. It's fine, I support that. I wouldn't have said anything either.
Yeah, I mean, I know the structure is because it finished the formal charges of oxygen.
Okay, that's fair.
I have a question on the formal charge. So you know you had like half 2 and half 6. How do you get the 2 and the 6 again?
Yeah, it's a great question. So for oxygen, it is the number of bonding electrons that are next to it. So formal charge is basically how many electrons can oxygen lay claim to? And it gets half of the 2 bonds in the electron. Alex will have you count the number of bonds. Both of those get you to the number 1. Whether it's half of 2 or 1, it gets you to the same place. You just need to pick a method that brings you, I don't want to say inner peace because that sounds like a lot, but a method that when you look at this, you always know the right way to do it because both ways are definitely valid. You just can't try to mix them together. Other questions? So next we're in a, I don't want to say a non-shocking twist, but it turns out that, like most things we have taught you some skill set, and now I'm going to tell you about how that is mostly a lie. So we're going to talk about resonance and exceptions or violations of Lewis dot structures. So if we look at this NO2 minus, you may have asked yourself, why isn't the double bond down here? Maybe that's where you wanted to put it. So it turns out that you could have drawn 2 structures. Could have also drawn this. Or this is B, and this is A. And in this case, the formal charges are going to switch. So resonance and more than one valid structure are kind of tied together. So we'll talk about what if there is more than one structure and how do we know if there's resonance. So both of these structures look the same, right? You just moved the double bond. So you could have drawn this, and I could have drawn this, and they're both equally correct. So a resonance structure, so some molecules have multiple equivalent structures. Now, these two look the same. If you were to, for this same molecule, have drawn this, So now we have two structures that look very the same. And this one that doesn't really, it's the same base molecule, but the charges are all different, and the electrons are in a different configuration. So they need to be equivalent. In your mind, equivalent should mean that you could rotate the structure and get the same thing. If you can't rotate it and get the same thing, then it's probably not a resonance structure. It's just a different structure. So resonance means something special. Resonance at heart means the electrons have multiple valid locations. So if we think about NO minus, and we start to think a little bit more about the bond. So we have a nitrogen-oxygen bond, single, and an NO double bond. If we were to take there are ways using X-ray crystallography where we can measure how far apart these two things are. We should technically get one long and one short, right? Because, well, why would we get that? Because that's what's in our structure. We have a long arm and a short arm. The reality is that the electrons move between this oxygen and this oxygen. So the resonance is saying that we get this, and it moves back and forth between them. Now, what that basically means is if you have this, this jacket's not meant for this. So we have long bond, short bond, and they move back and forth. So single bonds are longer than double bonds. The reason single bonds are longer is due to the change in electron density. If you have ever seen a hairband, like a hair rubber band, a regular rubber band, or a resistance band, if you've never seen any of these things, I didn't bring one to show you, but there's a loop of stretchiness. So in this, whether it's a resistance band or a hair tie or a rubber band, there aren't any in here. No one uses rubber bands. If you were to make it into a single loop, you have a lot of flexibility in that. If you make it into a double loop, it is harder to move your hands apart in two ways. One, it is harder to push apart, but it's also tighter together. If you try to wrap it a third time, and you shove your little hands in there, you're kind of going to do this. So every time you add a bond, whether it's a double bond, a single, double, or a triple, you increase the electron density. A triple bond is shorter than a single bond and much stronger. So in this case, we have a longer bond and a shorter bond. If you take a picture of this, what you expect is to find a long and a short, whether it's this arrangement or that arrangement. But we should be able to detect that. What we actually see is a mix of both, where we see this hybrid resonance structure that is a combined structure. So what we actually see, instead of a double and a single, is a 1.5 bonds. So it's an average between the longer bond and the shorter bond. We feel like this. I'm ready for vacay too. I promise we'll get there next week. Well, hopefully.
So the triple bond is the shortest, and it contains the biggest amount of energy?
Yeah, it contains the most amount of energy and the most electrons. Because it has 6 in a triple bond as opposed to 2 in a single or 4 in a double. Good question. Other questions? So, a resonance structure or structures is a visual arrangement of the different electron locations. What that means is that the electrons can be in more than one place. So, if you are asked to draw the resonance structures, you have to draw all the possibilities. So for NO2 minus, there are two possibilities. One here, one here. They should have the same base structure. You can't just redraw this structure 3 times and say, or 2 times. They should look in this arrangement. In Gen Chem 1, the majority of resonance structures that we're going to see involve oxygen. In organic and other courses, you're going to start to see carbon-based resonance structures where you can move a double bond around. We're not going to focus on that a lot, just want to present it in case you want to think about that. So let's look at the nitrate ion. So instead of NO2, now we have NO3, also minus. So the question often becomes, how do we know if we have to have resonance? If the molecule has resonance, do we have to draw them on? The answer to the second one is yes. If it has resonance, you have to draw them on. More often than not, it will say, for this molecule, draw any available resonance. Hallmarks that will say, we might have resonance. Usually, it's a central atom connected to a bunch of the same things. And the way you know how many it is usually based on how many different similar arrangements you can make. So the valence electrons here are 5 plus 3 times 6 plus 1, so 24. Got our nitrogen. This uses 24. Yeah. So we need to make a double bond. So now we have a double bond. Now we need to look at our formal charges. For oxygen A and B, OA is 6 minus half of 2 minus 6, negative 1. So both of these have a negative charge. OB is 6 minus half, 4 minus 4. That is 0. And what do we have left? Nitrogen. 5 minus half of 8 minus 0 plus 1. So the nitrate ion has a positive charge on the nitrogen and 2 negative charges, which cancel out to give you an overall charge of minus 1. How many different resonance structures do you expect? 3, because there are 3 oxygens that could contain the double bond. So when you draw those, we include what are called resonance arrows, which are a double barbed arrow, so arrowheads on both sides. And that means it requires no energy to get from one side to the other side. So from here, we have this. And we also have this. So these are resonance structures. Questions about resonance structures? Yeah.
Why do you do only 2 of the oxygen when there's 3?
Here. Because this one and this one look the same. So I would suggest, if they're the same, and we all think about how to be faster, if they are the same structure, you don't need to calculate the formal charge on both. Good question. You will also note that oxygen only has 2 conformations. It's either a double bond with 4 electrons, which is neutral, or a single bond with 6 electrons and it has a -1. It's really the only thing it does. If you're doing something else with it, it's wrong in purposes of this class. Very rarely we see a triple bond. Other questions?
So you have like the oxygens that only have like 4, have like a double bond,
Yes.
and then the dot around it. Is there a reason why you put them that way?
No. They should technically, so this one? Yeah, these should be over here. When we learn Vesper structures on Monday, when we go from 2D to 3D, the arrangements will start to matter, but in a Lewis dot structure, there are less constraints on the orientation of molecules.
So generally, it's like the one, the central one that we decided, we'll just go with the same structure.
This one?
Yeah, so would that be the main one, for instance? Or would that would be like the first one we came up with?
For this structure, you would have to present all 3 for full credit. So it's usually molecules with more than one oxygen. There aren't really, you can get resonance in other molecules, but more often than not, we see it with oxygen. So you need oxygens and more than one oxygen. Because you can't make, it has to look the same.
So could it be with 2 oxygens?
You could do it with 2 for like NO2 minus. You see it with, in a minute when we think about how some versions of these sulfite and sulfate structures have resonance. But for the most part, you have to have extra oxygens and you have to have a double bond.
What's the maximum amount of resonance structures we'll probably do?
4. Because you can only have the number of things connected to the central atom. So in this case, there are 3 equivalent structures that you could have up to 4. But you could have 2. It's either really a 2 or a 3 kind of situation. Other questions about resonance? So let's talk about when the octet falls apart. We know that it's going to. We've seen ideas that it might collapse. If we looked at the sulfite ion, which is the SO3 2-, some of you might have thought to yourself, I wonder if there's a way to get rid of all of the charges. You might have started your homework, and there are things that don't have octet. There are also molecules that have more than octet. And every now and again, the most rare of the exceptions is the exception where they have an odd number of electrons. Now, the reason this is an exception is because in order to have octet, you need to have 8 electrons. 8 is an even number. So if you have less than an even number, someone doesn't have octet. So the first exception is an odd number of electrons. We'll say a valence electrons. What we mean by that is that it has an odd number, meaning it has, I don't know, not even. Here are some examples. We have ClO2, we have NO and NO2. So for ClO2, it would be 7 plus 12, and that gives us 19. NO is 5 plus 6, which is 11, or 5 plus 12, which gives 17. So these molecules exist. Now, I just erased it, but we have seen NO2 minus. That had an even number. So some molecules adapt to just often have an extra electron. So let's look at structures for nitrogen monoxide, NO. We're going to do this one. So in this case, if we take our Lewis dot structure rules, we connected them, we're going to give someone octet. I'm going to give oxygen octets. So we've used 8, 9, 10, 11. So nitrogen does not have octet. In this case, I'm going to try to get closer to octet by creating a double bond. Now, I give octet to oxygen first. There's only 2 choices. Alternatively, you could have started with nitrogen and said 2, 4, 6, 8, 9, 10, 11. And so again, we are going to try to make octet by doing this. Now, this breaks a lot of rules. But in this case, when you violate octet by having an odd number, you still want to be close to 8. If you had left it apart, basically the previous structure, it would have been 5 electrons around nitrogen or oxygen. This gives you 7 and 8, which is better. Now, we've talked about resonance structures where it kind of, moves around. But in this case, one of these is going to be preferred. We have to calculate the formal charges. So the formal charge of nitrogen in this molecule is 5 minus half of 4 minus 3, which is 0. For oxygen, it's 6 minus half of 4 minus 4, which is also 0. That's a good sign. We know that we want to have 0. Now, it's possible that this will also be 0. I mean, not very likely. Nitrogen here is 5 minus half of 4 minus 4, which gives us -1. And oxygen is 6 minus half of 4 minus 3, which gives us +1. When we talked about formal charges, one of the ways that we want to reduce formal charge, so we prefer no formal charge. When we have to have it, we need it to be on the most electronegative atom. Which of these two is more electronegative?
Oxygen.
Thank you. Oxygen. So oxygen has a positive charge. So this is our preferred structure. This violates the formal charges. So we prefer our formal charges to be neutral, and we need oxygen to have the negative sign. Questions about molecules that have odd numbers of electrons. Of the different trends, so there are basically 3 violations of octet, this is the most rare. More often than not, we see it where it is either absorbed an electron or removed an electron to get to an even number. So let's look at, the second violation is where we have less than octet. So in this case, we have central atoms that do not have 8 electrons. We know that this is possible because we've said hydrogen's octet is just 2 electrons. It's not really a violation if it's just 1 element. So let's look at some other examples. So if we look at boron trifluoride, our number of valence electrons are 3 plus 3 times 7, which gives me 24. Put our boron in the center, add us some fluorines. So here, we've added all of our valence electrons, all 24 up there. Fluorine has octet, boron does not. The Lewis dot rules say, if it doesn't have octet, make a double bond. So let's do that. So now we have, everyone has octet. This makes the octet rule happy. Obviously, we're talking about violations, so let's talk about why this structure is not the preferred structure. It has octet, but it is not preferred. So here, let's look at the formal charge of boron. It's 3 minus half of 6 minus 0, which is 0. Which is a good sign. In this structure, boron is 3 minus half of 8 minus 0, negative 1. Fluorine A is 7 minus half of 4 minus 4, which is plus 1. So in the structure with the formal charges, 1, we have formal charges where they didn't need to be. But 2, fluorine is the most electronegative atom, and we just gave it a positive charge. So in the terms of BF3, the preferred structure is this, where we have boron, no formal charge on the fluorines. It turns out that on your periodic table, if you look at it, hold on, let me pull it out. Everything in the column of boron and all the way down, all of those can have less than octet. So much so that their octet is just 6 electrons. So boron, aluminum, gallium, indium, and we don't use the other ones as much, will all adopt this structure, where we have a central atom with less than octet surrounded by other atoms. If you were to draw a molecule using any of the S block elements, they also have less than octet. So if you were to draw a molecule, which we don't do a lot of, with magnesium, so MgCl2, its octet is only 4 electrons. So anything from boron to the left, excluding the transition metals, has the ability to have less than octet. Questions about either odd number of electrons or less than octet?
So why is the left one preferred again?
There's no formal charges here. And in this structure, fluorine, well, in all structures, fluorine is the most electronegative. And so here it has a positive charge. And so that, it's kind of a hierarchy of things that are bad. And so it turns out that fluorine having a negative charge and boron having a negative charge is worse than having less than octet. In chapter 9, we'll look at other reasons why this is true and more electronic reasons using electron configuration. But for now, so the last one, the last of the violations is where we have more than octet. So this is molecules where the central atom has 10 or 12 electrons around it. These are either considered, some people use the word expanded octet, or hypervalent. Both of these mean you can have more than octet. Now, you may have more in terms of 10 or more in terms of 12. There's no more than that. You can't have 16, you can't have 18, 14. It is basically less than octet, we've talked about those, but more than octet is either 10 or 12. So some examples of that are as follows. SF4, ASF6 minus, ICL4 minus, and PF5. So let's look at some of these examples. So first we're going to start with PF5. So first of all, we know for PF5, there are 5 things connected to our central atom of phosphorus, which tells us we're already over octet. So we can do the same Lewis dot structure rules that we've looked at, where we have 5 plus 7 times 5, which is 40. So we have a lot more electrons. So the Lewis dot rules say, count your valence electrons, connect them. So we're going to draw 5 things connected to phosphorus. We're going to add our fluorines. Then we're going to give everyone octet. So I've used all 40 of my valence electrons. So we're out, but the formal charge on fluorine is 0, and the formal charge on phosphorus is 5 minus half of 10 minus 0, which is 0. So none of these have a formal charge. If you look at your periodic table, and you find phosphorus, if you go over and down, these can all have expanded octet. Everything in the column with phosphorus can only have up to 10 electrons. As you go over, so sulfur, chlorine, argon, this does include the noble gases. Those can have up to 12 items, 12 electrons, around their central atom. So it's phosphorus and over, including noble gases, phosphorus and down. You need access to the d orbitals in order for this to work. You need more orbital space, which is not present in carbon, nitrogen, oxygen, or fluorine. Question?
Yeah, so you said going from phosphorus towards argon.
Yes.
Is that row or like all of them?
Everything, so all of these. If you have phosphorus over to the right, sorry, trying to talk with shapes. All the way over, including argon, everything in that row, but everything all the way down the periodic table as well can't have expanded octet.
Okay. So you said it was up to 10 for the row phosphorus?
The column phosphorus. It's okay. Phosphorus and arsenic can only have 10. But sulfur, chlorine, argon, and down could have 10, could have 8, 10, or 12. Yeah, so why don't you try ICL4 minus, where we have an iodine connected to 4 chlorines and a negative charge. Yeah.
And you took the boron excluding the transition nodes, that way they can have less than octet, right?
Yes. How many of you have a structure? Sweet. So the valence electrons here gives us a total of 36. We're going to put our iodine in the center. We're going to connect our chlorines. We're going to follow the Lewis dot rules. We are going to continue to add our electrons around the chlorines, giving them all octet. So here I used 32 of my 36 electrons. If you look in the guidelines, it says extra electrons go on the central atom. But up until now, the central atom didn't have octet. Here it does, but the rules still hold value. So we can add our 2 electrons here. We also know that this molecule has a formal charge, so we can determine the formal charge of iodine, which is 7 minus half of 8 minus 4, which gives us minus 1. Chlorine is 7 minus half of 2 minus 6, which is 0. So our negative charge resides on the iodine central atom. What questions do we have about violations to octet? Yeah?
On the eye, does it matter when you put the 2 dots, like can you put them on the left side or the right side or up top or on the bottom?
As long as there are 2 sets of 2 dots. I don't really care where they go in a Lewis dot structure. As long as you didn't do 1 dot, 1 dot, 1 dot, 1 dot in all of the empty quadrants, there is no wrong place for them to go. Good question. Other questions? Yeah?
When finding the formal charge, we just ignore like the charge on the actual thing, like the Cl negative.
So in this case, but the negative charge is only on the iodine. Are you asking if we should put it in brackets?
No, like when you do like the valence electrons minus half of the bonding, like for 7 for chlorine. Yeah, would you just ignore the negative charge on the compound?
Yes, for the purpose of formal charge. So you use the negative here, and then the formal charge, I don't want to say who owns it, but who gets to keep the idea of the formal charge. And in this case, it resides on the iodine. Good question. Other questions? For the remainder. So my guess is many of you are like, is it ever going to get easier drawing Lewis dot structures? Yes. Because everything we do in chapter 9 builds on Lewis dot structures. So we're going to draw, I don't want to say more and more, but by the time you take mini exam 6, you will probably have drawn 45 at least Lewis dot and Vesper structures. So it's okay if the rules feel kind of hard. Use your guidelines, follow them, and there are trends to which elements can violate octet. So the last thing we're going to talk about, we are going to get a nice throwback into chapter 5. If you own the textbook or read it online, the readings for this come out of chapter 5. So in chapter 5, I don't know, 3 million years ago, we talked about the many different ways to calculate delta H. And I said, there's one more, and we're going to see it in chapter 8. So it turns out that we can use calorimetry, we can use Hess's law, we can use heats of formation. This is what's called bond enthalpy. So bond enthalpy is going to think about other ways that we can look at bonds, the things that hold the atoms together, and figure out, maybe we can calculate the heat of reaction that way. So the strength and length of bonds. We briefly talked about when we talked about how in resonance we see a different structure. But if we look at a carbon-carbon single bond, a carbon-carbon double bond, and a carbon-carbon triple bond, the lengths of these are 1.54 angstroms, 1.34 angstroms, and 1.20 angstroms. So this is the same two atoms, so the difference is based on the electron density. You will not be asked to recall these data points, just to be clear. So in this case, we know that carbon-carbon single bonds are longer than a carbon-carbon triple bond. In addition to the length between them, it requires more energy to break them. So it takes 348 kilojoules of energy to break a single bond, 614 kilojoules to break a double, and 839 kilojoules to break the triple. If we have spaghetti noodles, which hopefully we've all seen, the long skinny ones, and if you have one, it breaks really easy. But if you were to have, okay, 3 breaks really easy too, but if you had like 300, it requires substantially more energy to get those to break. It's the same type of phenomenon when we think about how strong a bond is, whether it's a single, double, or a triple. We can store energy in bonds. So if a compound is explosive, they're often compiled or composed of a substantial number of triple bonds and double bonds, because those store a lot of energy in there. So if you can get them all to break at the same time, you can get an expansion of energy out of this molecule. So we think about this because it's going to help us when we start to draw in 3D. The other way we can really think about strength and length of bonds is to start to think about the calculation of bond enthalpy. So, bond enthalpy. It is the energy required to break a particular bond. So it is of note that these are all positive. And they're positive because the bonds, it requires energy to break them. What we know from enthalpy in general in chapter 5 is if it requires some number of energy to break it, it is the opposite numerically of that energy to put it back together. So we can start to think about that in this case. We are going to use the idea behind Hess's law, where we can put something together and take it apart. If we were to look at this reaction, where H2 plus Cl2 gives us 2HCl, we want to know delta H reaction. We could do this using heats of formation. We can also use this using bond formation. Now, the reason we talk about this in my class in chapter 8 is because bond enthalpy is about the bonds broken. So we need to know, what do the bonds look like in a Lewis dot structure? So for both H2 and Cl2, we could draw a structure. H, H, and Cl, Cl, with our lone pairs. So now we have two structures. We want to look at bonds broken minus bonds formed. Oop, we forgot to draw our product. So we have an HCl. So we want to take apart the HH compound and the ClCl and basically make two new compounds, or make two new bonds. So bonds broken, we're going to break one HH and one ClCl. And we're going to form two HCl. Now, you might be tempted to say, well, we need two hydrogens. They are connected, so when you break them apart, it goes from one item to two. You should, let me grab my copy. On the back of your Lewis dot structure page are a list of bond enthalpies. So using this information, we could say, all right, HH is 436 kilojoules, and the Cl-Cl bond is 242, and the HCl is 431 kilojoules. So we want to subtract broken minus formed. So in this case, it would be 678 minus 864. I don't think that's right. So we get negative 186 kilojoules per mole. So the bond enthalpy is just a different way to calculate delta H using the structural information. Yeah.
Isn't it 862? Yeah.
I don't know. Apparently. That calculator doesn't work, like the buttons stick. So what is the next one? Minus 862. Thank you. If you do the math correctly, this is what you get. This reminds me of Legos, where you have to take it apart to build something new. Requires some number of energy to collapse the structure. The other part puts it back together. So, previously, it has always been products minus reactants. This one is broken minus formed, which is reactants minus products, because they are all positive. Questions thus far? This table, which is the one on your sheet. Please don't memorize any of these tables, any of these values. I feel like we should cover that. Like everything else, I will give you a table. It will say, using the data in the table below. The parts of this that are hard is making sure that you pick the right bond. Places when they are different is if you have multiple bonds. They have a stronger energy. In this graphic, they're at the bottom. I will mix them all together. So if you have a carbon-carbon double bond, it's not 2 times a CC bond, a single bond. So let's look at some examples. So in this case, we'll leave that up. If we have methane gas, so CH4 plus Cl2 gives me HCl plus CH3Cl. So the reason we held this is because now you can be asked to draw a Lewis dot structure, then determine broken minus formed. So we'll start by drawing methane, which is CH4 plus Cl. So we know that we're going to break 4 times carbon hydrogen and 1 chlorine chlorine. Over here we have HCl. We have CHCl. So we're going to form 1 HCl, 3 carbon hydrogens, and 1 carbon chlorine. So then you just read the values off of the table. What questions are percolating around your brain in this moment?
I have one question regarding the enthalpy.
Yeah.
Since they're always positive, are we reporting it as a negative?
Well, in this case, if it's broken minus formed, If it is negative, that means it is an exothermic reaction. So that is the delta H reaction. It's kind of like back in chapter 5 if you did heats of formation. Sometimes the numbers were positive and sometimes it was negative. The reason it's not products minus reactants is because they're always they're always positive. So whatever that number is, broken minus formed, whether it's negative or positive or zero, won't be that. You report it as is. Good question. Other.
So literally, like when you write the break-in forms, you're really just basically putting the loose dot structure, but like just into like numbers and bonds.
Yes.
Okay.
So the idea is that you would take each of these and you would break this one, this one, this one, that one. And then you just account for all of those energetically, sum this up, subtract from this, and that's all there is. Other questions? So in this case, the delta H of the reaction is negative 104 kilojoules per mole. Yeah.
Because it's 4CH, would you do 4 times the 415?
Yes, it will be 4 times 415 or whatever else it is. I personally prefer to write out all of the broken and all of the formed. I don't want to say counting is not my strong suit, but you are more than welcome to say, hey, we're going to put back together 3 of these and do 1 here and none of these here. I find that stuff gets lost in the shuffle when I try to do this. I don't actually recommend it, but it's not wrong. Is the point I want to make. In the time remaining, why don't you, using the sheet and the structures up here, which hopefully you can see them, on the mini exam, it could be presented in one of 2 ways. One, it will be an equation, like a chemical equation where you draw the Lewis dot structures and calculate it. Alternate 2, if I want to pick something you've never seen before, I will give you Lewis dot structures. And say, using the following Lewis dot structures, calculate the bond enthalpy, or use the bond enthalpy below. How many of you have gotten an answer? How many of you are very close to an answer? Give you another one. How many of you have, well, would anyone like to share what answer they got? Yeah.
I got 57.2.
I did not. So, in here, there are 6 carbon-hydrogen bonds multiplied by 2. So that makes 12 carbon hydrogens at 348 apiece. There are, nope, that's 413. There are 2 carbon-carbons at 348, sorry. There are 7 oxygen-oxygen double bonds at 495. When I add all those up, I get 9,117. For carbon dioxide, there's 4 CO2 molecules, each with 2. So that gives you 8 CO double bonds at 799 a pop. And so there are 12 OH bonds at 463. So I get 11,948, which gives me a delta H of negative 2,831 kilojoules. Question. Did anyone, what questions do we have about this calculation? Can you say that again? So this 2 also breaks 2 of them. It's a good question.
There were 7 double bonded oxygen, right?
Yes. If you have other questions, I'm happy to answer them. Otherwise, I will see you all on Monday for Chapter 9.